today at a chapter on forces. I'm going to start off by looking at force diagrams. First things first, following on from feedback from other videos I've done, apparently the covering for my table wasn't to people's likings, so I've just gone for the table itself today. So as I'm listening to my fans on YouTube, and doing the best I can. So let's have a look at force diagrams then. I've got a few examples to look at. We're going to draw some pictures and talk about the sort of forces, the sort of phrases that you can be looking for when you do your diagrams. Diagrams are key to a good mechanics solution. So example one says we've got a book of mass n kilograms on a horizontal desk. Not a great deal going on with this one. We've got a desk, got a book there. We're going to have the weight. Don't forget m, its mass isn't a force, but n times g is. And because the book is in contact, we're going to have a reaction force. A reaction force is always perpendicular to the surface. In this case, there's nothing else going on. There's no other forces on it. Whether the desk is rough or not, is not appropriate here. Notice, I see pictures sometimes where the forces have got the units newtons on. I tend not to do that because I'll always get someone who thinks that m all of a sudden is in grams when I put mg. So mg is a force, mass times gravity. We'll take g to be 9.8 unless you're told otherwise. Example 2, beach ball, mass 0.8 kilograms, is thrown upwards but is moving downwards. Now, beach ball, in reality, all it's got is its weight, 0.8 g. There might be some form of air resistance going upwards, but we generally, in our early part of mechanics, look to ignore air resistance because it's partly because it's hard to measure, and we're only starting off by looking at a rough mathematical mechanical model. As you go through a course, we might look at the way the body moves, the size of the particle, the centre of mass of the particle, what effect these sort of things have it on at the moment. But because we're tending to treat them as point masses, we're not really interested in the air resistance. So in reality, that's the only force acting on it, which is weight acting downwards. We've got a box of weight W on a rough horizontal surface pulled by two tensions T and S in the same direction. So we've got a rough surface, there's my surface, there's my box. My boxes and my surfaces tend to look pretty much the same. And as before, we've got weight W, we've got reaction. Where possible, it's quite odd because we're treating the body as a point mass at the moment, even though we're showing the physicality of it looking like a box. I tend to have my reaction and my weight acting through the centre of mass, my friction acting where the box and the surface meet. So if I've got both T and S going that way, we'll have a friction that opposes the motion going that way. I like to write F with a little R for friction, and not R for friction, but FR for friction, to differentiate it from F being a driving force from F equals ma. All these things we're going to use later on, but sometimes I've seen students use F equals ma, use F for friction, and so friction equals mass times acceleration, which isn't going to happen when we see it later on. So those are my forces then. I've always got the reaction. In this case, I've got a friction, got weight, and the friction opposes the motion because we're pulling it that way. If it's moving at all, it will want to move in the direction of T and S. Okay, three more examples. A crate of mass, 40 kilograms. We've got two ropes given in vector form, I's and J's, minus 84,205 and 84,187. And the thing is held in the air. So we've got this thing here. We've got 40 kilograms there, so its weight is 40g. We're going to have minus 84,205, means 84 back and 205 up. It's acting in that direction there, and just write it as a column vector, minus 84,205. And then this one is in this direction here, 84 along and 187 up. So 84 187 there. And since it's held, it will be in what is called equilibrium, which is where all the forces balance out. So I've got the 84 acting that way, the 84 acting that way, they cancel each other out, and 205 and 187, I'm hoping when they add up together, 385, 392 is equal to 40 times 9.8, so the upwards forces, the 205 and 187, are balanced out with the downwards force. The force going left, the 84, equals the force going right, 84, so everything cancels out. Whereas in this case, pushing a sofa mass 80 kilograms, there's a resultant force, so it's in motion, it's moving, it's accelerating. So we've got our rough floor, you know what, it looks just the same as my box did before. I've got mass 80 kilograms, so I've got 80g. It's in contact with the surface, so I've got a reaction. I've got a push and a pull actually going on, 120-25. Now, even though it's being pushed, I tend to like to draw my forces going out from the body. So even though this is 120 along with 25 down, so acting like this, in that direction, what I'll tend to do, I'll tend to show it going out from 120 out and 25 down, like that. So there's my 120 minus 25. 73.30 is 73 along with 30 up. So it's that way like that. And so in that case there, because it's rough, I've also got a friction opposing the motion like that, so FR. That's my diagram then. So where possible, show your forces so you understand. If I would have left that 120 minus 25 there, it just makes it awkward when I'm looking to resolve. I like my forces going out, so I know that my force to the left and my force to the right, if there's a resultant force, it's going to go that way. If there's no resultant force to balance out, it's not accelerating. Here we go. Example 6. A calculator on a rough slope, angle at 30 degrees to horizontal. So here's my slope, 30 degrees. Here's my calculator. You know what? It looks just like the same as my sofa did, my box did, and so on like that. And so, centre of mass there. My weight acts vertically downwards. Not told what it is, let's call it mg. My reaction acts through the centre of mass now. What I'm going to do, this will be useful later on, is extend that line back that way and put in there 30 degrees. In fact, I might even put a little arrow on there. At some stage we're going to have to do something called taking components. We're going to have to resolve this weight into components that are perpendicular to the surface, i.e. opposite to the R, and parallel to the surface, that way there. Now, if this is the situation, the weight component acting downwards would mean the thing was moving downwards. What potentially stops it moving downwards is the fact it's a rough slope, so the friction, since it wants to go downwards, will oppose the motion like that. Okay, so those are my three forces there. There's a link between the angle and the friction. Basically, friction, as you tip this surface here, it starts off at 0, like in example 1. And as you begin to tip it, the value of friction will get bigger and bigger and bigger, depending on the size of the angle, until it reaches what is called limiting friction. And at that point, that's the maximum value of friction can be. Any angle that's steeper than that will mean the thing is sliding along. If I, for example, put my pen on here, or something a bit rougher than the pen on here, and began to tilt it, there'll be a particular point where it would begin to slide down. And a steeper angle than that means it slides down quite quickly. But we'll look at friction and angles later on. Last couple of examples. We've got a smooth plane of 28 degrees to the horizontal. We've got a block of weight W newtons, and a thrust, a horizontal thrust of 7 newtons. Here's my plane. You know what? It looks just the same as it did before. I've got 28 degrees there. I've got centre mass. I've got vertical weight W. I've got a reaction, as always, there. I go dot, 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 dot. I put my 28 degrees there. one little arrow, and it's smooth, so there's no friction. But the only thing stopping it going down, it's held in place, is a horizontal force, 7 newtons going that way there. Okay, so W and 7 are perpendicular to each other, and if I need to put on angles for the 7, I'd actually put in there, that one there is also 28 degrees. It's the same as that. But 28, 90 minus 28, and 28 there. So when I'm looking at components, I've got the 7 Newton force, and the 28 degrees will be part of it later on. And your last one for now, ladder. Here we go, uniform ladder on rough ground, rough wall. We're not told a massive amount about it, apart from the fact of the keywords. So I tend to, because I've got solid things that aren't going anywhere, I'll do that to tell me that they are not in motion at all. There's my ladder. Right. I'm not told what the mass of the ladder is, but so we'll call it M. Because it's uniform, I know that it's going to act at the centre of the thing itself. Now, ladders and rods, part of what we're not going to treat this as a point mass all of a sudden, because this is in contact at 2 different parts and 2 different ends here. So the length of it does have a relevance. When we had our calculator, our block, our sofa, we're treating those as a point mass here, but we'll begin to use these as a more sort of one-dimensional shape having a length. And as such, to show that we're using the centre mass, I'm going to refer to the length of it being something that we can halve, like 2A or 2L. If it's 2A, I'm going to mark on the lengths A and A there. The length will have a relevance to what we can do with it to solve various things. So there's my weight, mg. Where it's in contact with the floor and with the wall, there'll be a contact force, the reaction, and because both of them are rough, there'll be a friction. So what I'm going to do to show the difference between the two, I'm going to have, avoid my A there, that should be vertical. I'm going to call that one R1, and that one R2. It might be the same. Chances of both being the same are quite slim, to be honest. It depends on what else is going on. Now, the ladder itself will want to slide down the wall and go away from the base of the wall there. So to stop it, my friction will act at this point towards the wall, let's call it friction 1, and it will act upwards, that way there, let's call that one friction 2. So they are 2 different frictions because they are 2 different surfaces, and there'll be 2 different values as well. So we're treating, as I say, unlike these which are point masses, the length of this ladder is relevant, so we begin to introduce what the length is into it. My force diagram though has weight, 2 reactions and 2 frictions. And that's a little bit about how we start off looking at drawing force diagrams so we can use them later on.